Okay, it is 10 o'clock. Hello, everyone, and welcome to our Lakeside Kids online series. I'm Misty Lorenz with Monona Terrace, and our special guest today is Jeff Holt, Director of the Madison Metropolitan School District Planetarium. I'm so glad you're able to join us for this morning. It's our first program of the Lakeside Kids series, and the topic is Introduction to the Planetarium and Summer Night Sky. Before we begin, we have a few items to cover with everyone. The chat function has been disabled for this webinar. We will only be using the Q&A function. Click the Q&A icon on your screen and type in the text box that appears. We'll be taking questions throughout the presentation. A copy of today's program will be posted on the Lakeside Kids page of Monona Terrace's website. And last but not least, we'd like to thank Dane County Arts with additional funds from the E&S Manufacturing Company Foundation, the EVU Foundation Incorporated, charitable arm of the Capital Times, the W. Jerome Brauchi Foundation, and the Pleasant T. Rowland Foundation for sponsoring this program. And now over to you, Jeff. Welcome.
All right. Well, thank you very much. So happy to be gathering with all of you today. I wish that we could be gathering under the dome in the planetarium, but hopefully we'll be able to do that someday soon. But it's a beautiful day outside, and what I want to do with you today is to explore some of the things that you can see on nice clear days like today and into the night. This time of year, you have to wait until it's pretty late in order to see the stars. So actually, the fact that I can show you the stars in here today might be the only stars you're going to see for a while if you are a young observer. But don't worry, in a few days, it'll be the summer solstice, June 20th. And after that, the sun will be setting earlier and earlier each night, and we'll give you a preview of how that works in our program today. I also wanted to give you a little bit of a sneak peek at behind the scenes, so that I'm going to share with you a video tour of the planetarium and its capabilities. And if you watch carefully in the tour, you'll be able to see things that you don't normally see when you go to the planetarium. At the beginning of the tour, you're going to see my hand kind of poke into the view of the video, and I will be starting up the servers, the machines that run the magic that we see in the planetarium. So watch for that. And also, you'll get a chance to see behind the console all of the buttons and things that we use to simulate the sky in the planetarium. All right. So without any further ado, we're going to share with you that video tour of the planetarium. Also, there will be text. If you have young readers in the at your location, you might want to read the text. All right, and if you have any questions about the planetarium, go ahead and put them in the Q&A. We do offer programs for the public on a monthly basis. When we can do in-person programs, tickets go on sale online, typically 2 to 4 weeks before the program starts. But when we haven't been able to do in-person programs, we've been offering virtual monthly programs, and we will continue that again in the fall if we can't meet in person. Now, I did see one question come up during the video tour, and that was about how craters on the moon are made. And so just a quick answer, that's actually every place where you see a crater, like a bowl-shaped hole like this. That's a place where a space rock has smashed into the moon. And the energy of that impact just blasts away all of the rock that was in that location, and it leaves that bowl-shaped hole. Thanks for asking. All right, now there's something that I want to kind of preview for you before we start looking at a simulation of the night sky. And that would be star patterns, like the shapes that we see. You know how if you are outside on a partly cloudy day, you can see, individual like puffy clouds. And sometimes we look at them and we say, oh, that cloud looks like an elephant. That cloud looks like a dinosaur, using our imagination. Well, when we look up at the night sky, sometimes the stars remind us of shapes too. Like there is a star pattern that we call the Big Dipper, where they're grouped together in a way that reminds us of things like a ladle or a pan or a spoon like this. Back in the old days, people would use a dipper like this with this curved handle and this part we call the bowl, made out of stars. And so that is a common star pattern that we will look for in this program. And I'm going to encourage you to look for outside on the next clear night. Now, it could be at any angle, not always right side up, could even be upside down. Now, I'm going to use 2 pieces of software to simulate the sky. The first one I'm going to use is called Stellarium. And one of the reasons I wanted to use this one is this is one that you can actually use at home. It's free. If you just go to stellarium.org, not right now, but later, then you could either download the software to your computer if you have a computer that could do that, or if you have a Chromebook or a tablet, you could go to stellarium.org and click on Stellarium Web, and you'll be able to do almost all of the same things that we're going to do here today. And then when I was showing you like the capabilities of the planetarium in that video, when we were flying to Saturn or flying to Jupiter, those are things that we can do with our Digistar simulation system. And the cool thing about it in the planetarium is that that simulation is covering the entire dome. So it really makes us feel like we really are traveling to Saturn or to the moon. So we'll show a flat screen version of some of those explorations toward the end. All right, let's switch over to Stellarium. Now, Stellarium is what you would call a planetarium program, because just like a planetarium, like that room that I was talking about in the video, it simulates the sky, and we can set it for whatever location we want. I do have it set for Madison, Wisconsin, planet Earth. Yes, you can set it to show you what it would look like on other planets. And then I have it set for today's date. Here's the year, the month, the day, and then this is the time. Now, this is in a 24-hour format. So 20 o'clock is 8 p.m. Notice that it's 0 minutes and 0 seconds. And because you don't see the seconds ticking away, you can see that I'm holding the time at 8 p.m. tonight. Now notice that this is 8 p.m. and what we're seeing is a beautiful blue sky. And in this case, it's a grassy field for our horizon scenery. Now, the horizon is what we call that line here, where it looks like the sky touches the ground. And along the horizon, you can see compass directions. This is S for south, southeast over here, because east is over in this location. So southeast is in between east and south. Then over here, you can see the west. This is south, southwest in between. And you can see kind of the glow of the sunset over here. It's not sunset yet, but this scene includes things like trees and houses like you would have for real out there in the real sky. But I want to show you something that will be over here in the west and northwest part of the sky that we would want to see all the way down to the horizon. Now, since that might not be realistic where you live, you might have to travel to a place where you can see all the way down to the horizon. And to do that in Stellarium, what we have to do is we have to go into the settings here and go to the landscape settings, and we're just going to click 0 horizon. And that takes away the pretty scene that we had, but that allows us to see all the way down to that line that we call the horizon with no trees or houses. Now you can see the sun. And you can see that even at 8 p.m. tonight, the sun hasn't set yet. This time of the year, the sun sets really late. 8:39, I think, is officially the time for sunset here in Madison. I'm going to go ahead and start the clock. Now, if you look down here, you can see the seconds are ticking away. So now, since we said that 8:39 is sunset, all we have to do is wait 39 minutes and it'll be sunset. Oh, and then we have to wait another hour and a half for it to be dark after that. Don't worry, we're really not going to wait that long. Another feature of these planetarium programs is that we can fast forward through time. Now I'm using keyboard shortcuts, but there are settings down here. You can see that's a fast forward button. If you want to know the keyboard shortcut I'm using for your own use, I'm hitting the L button. Every time I hit L, we're going fast forward even faster. Now the minutes are going by like seconds, even a little bit faster than seconds. Notice that the sun is about to set right around 8:39 like we talked about. And then the sky is still too bright for us to see any of the stars. And so in order for us to see things that look like stars outside, our sky has to be darker than the stars. Now, I've set it back to normal time right now by hitting the letter K on my keyboard. And so now you can see the seconds ticking away. It's around 9 o'clock, and we're already seeing something that looks like a star. Now, you can tell by the fact that I'm saying it looks like a star, you might guess that it's not a star, and it's not. If you go out on the next clear night and you can see low in the west and northwest, the first thing that you'll see that looks like a star after sunset is not a star. It's sometimes referred to as the evening star or the morning star because it's the when it is up in our sky, it'll be either up above the sunset or up above the sunrise, and it'll be the first object we'll see in the sunset or after sunset. And then if it's in the morning sky, it'll be the last thing that we can see before the sky gets too bright for us to see anything out in space besides the sun and the moon. All right, you might have already guessed which one it is, but it's the planet Venus. Now, as I click on it, it'll put the name up here in the upper left. So Venus is the brightest planet for two reasons. It's fairly close to us, even though it's not at its closest point to us right now, but out of all the planets, it's one of the closest. And it's covered with white clouds that reflect a lot of sunlight back at us. And so Venus is a bright planet. Now, Venus is going to be up in our sky throughout the whole summer, throughout the fall, all the way into December. So you'll have lots of opportunities to not only find it in the sunset, but to teach your family and friends how to identify Venus. Now, as we go a little bit later into the night, we'll start fast forwarding some more. You'll see that Venus is getting lower and lower. So that means that if you go out later than 9 o'clock, you'll have to see lower and lower in order to still catch Venus. Notice that as the sky gets darker, we start to see more and more stars because now the sky is darker than the stars. Now you can see a beautiful crescent moon coming into view. Now by about 10 o'clock, the sky will be dark enough that we can see star patterns, even though it's not fully dark yet. It won't be fully dark until almost 11 o'clock. Isn't that crazy? All right, Venus is now very, very low in the northwest, but there's another planet that we can see too. Now, it's going to be hard to really pick it out and notice that it's different from the stars. But if you look in this field of view here, look and see if you can find something that looks a little bit more orange. It's a planet that has a reputation or a nickname of being the red planet, even though I think it looks kind of orange. Did you pick this one? There are some stars that look like they're kind of orange. And in fact, I'm not seeing any good examples in this field of view, but some do look orange. And so the other way that you kind of tell that this is a planet is by watching it really carefully and making sure that it's not twinkling as much as the stars are. Now, these two stars to me kind of look like twins, and the line of them is almost like parallel to the horizon. And that would be another way to help you know that you found the planet Mars, because these two stars and Mars are kind of lining up with each other right now. And so I will go ahead and click on it, and that'll confirm that it is in fact Mars. Now, there are apps that you could have on a cell phone that would also allow you to kind of aim your cell phone at different parts in the sky, and that might help you to confirm that you found Mars as well. But watch Mars very carefully, and if you just kind of stare at it and then stare at these two stars, they're actually the heads of the Gemini twins. Their names are Pollux and Castor. Watch them and then watch Mars, and out in the real sky, you'll see that Mars doesn't twinkle as much as the stars do. And you have to look for stars that are about as high as Mars is in the sky. So that's why I'm suggesting using the twins. So just remember, like the song says, twinkle, twinkle, little star, not twinkle, twinkle, little Mars. So 2 planets to look for in the evening sky. Now let's look for that star pattern that we call the Big Dipper. You'll always find the Big Dipper somewhere in the north half of the sky. And sometimes you'll see it nice and low. And as I drag my, my cursor down, we'll see higher and higher in the sky. Now I'm actually going to expand our view a little bit, zoom out, so that now we can see a line here, or a marker for the part that would be directly over our head outside. It's called the zenith. That's why it's labeled with a Z. Now, if we're looking in the summer toward the part of the sky that's almost directly overhead, then we would be able to see the Big Dipper. Now, in the winter, the Big Dipper would be way down here, low in the north, and you might not see it because, again, you might have trees or houses blocking your view. But look way up here, see if you can find that Big Dipper shape. In case you haven't found it yet, I will tell you that in the way we have this kind of oriented, looking toward the north, the handle is pointing up above my arrow. Here's the end of the bowl. Here's the end of the handle. So here's the handle. Here's the bowl. That's the Big Dipper. Now, we could look toward the south and find it, but if you look toward the south and then you look up higher and higher to see it, you would actually have to look a little bit past the part of the sky that would be directly over your head. Don't fall over, be careful. But now the handle looks like it's pointing down. There's the handle, there's the bowl. Now we can use the Big Dipper. Let's actually go back to the north. Sorry about spinning that around. Let's look back toward the north again. Here's the Big Dipper. We're going to use the Big Dipper to help us find other things in the sky, like a pointer, like these two stars at the end of the bowl. If you kind of connect those lines as like an arrow, that arrow could point either down this way or this way. Well, if you go out the top of the bowl, those two stars point to a star here that's right above the N for north. So that star, throughout the night, throughout the day, actually throughout the entire year, stays right here above the N for north. I'll bet you guessed which star it is. It is the North Star. Now, the North Star has a name. It's called Polaris. Pole star is what that means. The reason the North Star is always in the north, even though we're on a spinning planet that's orbiting around the sun, is that it's right up above the Earth's North Pole. So that even as the Earth is spinning, the North Star still stays in that same spot, right on the axis of rotation. Now, I've seen a couple of questions come in the Q&A about things that we're talking about here. Like we've talked about stars and planets now. And two of the questions were, how are planets made and how are stars made? Well, they're actually made in the same process. Out in space, there are huge clouds of gas and dust, beautiful nebulas. That's what we call them. And what happens is if there's one part of that cloud that's a little bit more dense, meaning there's more stuff in that area, then gravity can cause the gas and dust in that area to collapse. And what happens is that it forms a star, and then leftover stuff that was part of that dense area that kind of came together to make the star, the leftover stuff can clump together to make planets. So planets and stars are made out of gas and dust, and they're formed because of gravity. All right, let's look over here in the west again. And you can kind of see the Big Dipper here, right? We used these two stars to point to the North Star up here. We can also imagine that the Big Dipper is filled with water. And if we poke a hole in the bottom of the Big Dipper, the water would drip onto the back of a ferocious animal. It's one of those constellations. Notice that I didn't call the Big Dipper a constellation. It's a star pattern. It's an unofficial star pattern, and people around the world have actually different names for that star pattern. People in England call it the plow. In other parts of the world, they call it the cart or the wagon or the saucepan. So there are different names. Now, astronomers all over the world call the constellation that the Big Dipper is in. I'm just going to click on one of the stars in the Big Dipper so that the software knows which constellation I want it to identify. I'm going to put in the name. It's called Ursa Major. Major means big. Ursa means bear. And so if you connect some of the dots, you can maybe make some legs down here, the body of the bear. This can be the head. You might imagine it a little bit differently. I actually do. imagine it a little differently from this. And then artists have depicted the way they imagine the bear, and we can add in some of that artwork as well. So the official constellation that the Big Dipper is in is called Ursa Major. Well, this next constellation that I'm going to point out is an official constellation. Poke a hole in the bottom of the Big Dipper. The water drips onto that ferocious animal I was talking about. And part of it includes this thing that looks like a backwards question mark, kind of a hook shape here. Well, that outline, that backwards question mark, is the outline of the mane of this ferocious animal. So the fact that I called it a ferocious animal and it has a mane, you might actually figure out that it is a lion. I'll click on the brightest star in this constellation, the dot of the backwards question mark. It's called Regulus. And now I can bring in the name. Leo is the name of the lion. Now, to me, with the water dripping onto his back, that would be his body. That's his head, because that's the outline of his mane. And I imagine Leo laying down. So his tail would be here. And I just imagine that his back legs would be tucked up against his body here. And then from here, his front paw would be sticking out like this. But most of the artists draw the lion standing up. And hey, if you're the artist, you can draw it however you want. And we each get to imagine the lion however we would like. Now, Leo is a good spring constellation. But since we're still at the beginning of summer, we can still enjoy Leo in the early part of the evening. But remember how the planets, we saw them getting lower and lower over here in the west? And so later in the evening, Leo is going to be getting lower and lower. Now that happens because we live on a spinning planet. The Earth spins, and that makes the sun look like it rises in the east and sets in the west. The stars seem to do that too because of the Earth spinning. Now let's look for some more star patterns. Let's look way up high again to find the Big Dipper. So we went this way out the top to find the North Star. We went out this way to find Leo. Let's use the handle. You see how the handle forms kind of like an arc? The phrase I use is follow the arc to Arcturus. So go beyond the end of the handle with that same arcing motion until you get to a bright star. And that bright star is called Arcturus. Now, Arcturus is in a constellation that I think looks like an ice cream cone. Now, I don't even try to connect these lines here, but doesn't this kind of look like a sugar cone? So it's like that pointy type of ice cream cone and just a little bit of ice cream on top. Now, to me, I imagine that that there was a second scoop here. Maybe it was eaten, or in a minute, I'll give you another possibility. Now, you can imagine, since these constellations are ancient, they didn't have ice cream cones back in the day when they made up this star pattern. So today we might make up a name like Ice Cream Conius, but they called it actually Bootes. Bootes, the herdsman or shepherd. I still think it looks more like an ice cream cone. But here's the artwork for Bootes. Now, I think that instead of the other scoop here being eaten, I think it looks like the second scoop fell off, because right next to it is almost a full circle of stars here. And if you let me name it, I would call it Second Scoopius. But it's actually called, I'm going to click on the brightest star. Now, I know it by Gemma, but there's another name, Alphecca, for that. But I like to call it Gemma, which is another name for it, because it looks like the gem in this crown. You see, the name of the constellation is Corona Borealis. Corona meaning crown, Borealis meaning northern. And to me, it looks like a tiara. So I don't even try to like close the circle. But the artwork often shows a full circle type of crown. Now, if the second scoop falls off the ice cream cone, you can't eat it. You have to pick it up and put it in the wastebasket. Well, there's a wastebasket shape right next to it, and also known as the keystone. But I see it also as a capital H. Here's one side of the H, here's the crossbar, and here's the other side of the H, kind of a stylized H. But that could be the H for Hercules, because this is Hercules, the strong man. Now, this is a technique that we call star hopping to help you find a dim star pattern by finding something that's brighter first. So think about what we did. We followed the arc to Arcturus to find the ice cream cone shape. We found the second scoop next to it, and then the wastebasket next to that. And that can help you to find some of the dimmer constellations using techniques like that. All right, let's get rid of those lines. And I see a question in the chat. How does a star burn out? That's a good question, since we talked about how stars form. And stars, the way they shine is because there's so much gravity. Gravity is squeezing in so hard at the center that it's causing atoms of hydrogen, which don't like to stick next to each other. They hit each other so hard that they combine in a couple of steps to form something called helium. And energy is given off in that process. And it's that energy that we see coming from the sun that makes the sun so bright, that makes that heat that we feel on our face when we're outside with the sun shining on us. And if you were close to these other stars out in space, they would look like the sun too. Very bright, very hot, giving off a lot of energy. So I said that that energy is given off because the hydrogen is turning into helium. Well, eventually you can run out of hydrogen. Now, if the star is massive enough, it can actually fuse the helium into heavier elements too. But if, like for the sun, when it runs out of hydrogen, it'll start doing some helium and it'll expand to become a red giant. And then eventually it will contract to become a white dwarf, and then slowly cool over billions of years and eventually become just a dark cinder in space. The more massive stars, I said, can fuse hydrogen to helium, and they can fuse heavier and heavier elements all the way up to iron, but they can't go past iron. And so if you get enough iron at the center of the star, the core collapses and all of the other layers come crashing in on that core, and the star blows itself apart. That's called a supernova. So that's two ways that stars can burn out. Now, stars can seem bright for a couple of reasons. The same as planets can seem bright for a couple of reasons. So I see a question, why are planets brighter than stars? Well, not all of the planets are. I won't be pointing out Uranus or Neptune because we can't see those without a telescope. And so it's only the bright stars, or the bright planets, that we can see without a telescope. That would be Mercury, Venus, Mars, Jupiter, and Saturn. Now, a planet can seem bright because it's close, like I mentioned with Venus. It can also seem bright because of its color. And I mentioned that Venus is covered with white clouds that reflect a lot of light. You can imagine that if a planet was covered with something that was like the color of my shirt, it wouldn't be as bright. But if a planet is far away, that would also mean that it would be dimmer. But there's one more thing: size. Like Jupiter is much farther away than Venus, But because Jupiter is so large, it can appear almost as bright as Venus. Jupiter is the second brightest because it's covered with light clouds and it's so big. Now, stars are the same way. They could be giving off a lot of light. They could be big. They could also be close. Those are all the ways that a star could seem bright. Now let's look over here in the east. If you go out on the next clear night and you look for the three brightest stars in the east, they form what we call the summer triangle. So three bright stars in separate constellations: Vega, Deneb, and Altair. Now, if I turn on the constellation names, you can see that they're in separate constellations: Lyra, Cygnus, and Aquila. And I can turn on the constellation lines. Now, for this, it looks like a rectangle that somebody sat on. We call that a parallelogram with Vega next to it. This one, I think, actually looks very much like what it's supposed to represent. It's a bird. So is this, but I think it's a little bit harder to imagine, at least the way those lines are connected. But this is Cygnus the swan, with the head at this end, the tail at this end. And so these beautiful wings stretching out like this, I think it makes a very good swan. Lyra is a harp that you would hold in your lap, not a big one that like you would see in an orchestra. It's called a lyre. And then this is Aquila the eagle. Now that's not really the way I imagine Aquila. If I get rid of the lines and the artwork, I imagine this as the eye of the eagle, and then this could be the beak. Or if you want to imagine the eagle facing this way, you can imagine this as the beak. And then I see wings coming out here and here, and then the legs coming down here. But again, you can imagine these however you would like. Now notice that since this is the beginning of the summer, remember the sun was setting in the west, and at the same time the sun was setting, the summer triangle was just rising. So they're in opposite directions from each other. So that means that at the beginning of summer, the summer triangle is up all night long. And if we go into like late summer or fall, you'll see that they won't be opposite each other anymore, sun and the summer triangle. Now, remember, I'm showing you 10 o'clock. And if we start fast forwarding, remember we said that because the Earth is spinning, it makes things look like they're rising in the east. Well, that's happening because the Earth is spinning toward the east. And if we looked in the west right now, things would look like they're setting. So the summer triangle throughout the night would get higher and higher in the east. And as the sun is rising in the morning, the summer triangle would be setting. But notice also this thing that looks like kind of a milky highway across the sky. Summer is a great time to see this feature that we call the Milky Way. What we're seeing is actually light from stars way far away in our galaxy. Now, all of the stars we've been talking about are in the Milky Way galaxy. But what we're seeing here is light coming from stars that are so far away that we can't see any individual stars. We just see the combined glow of the stars in that region. And you see the dark patches? Those aren't areas that are like void of stars. Those are actually clouds of gas and dust, like we talked about. And the dust is actually obscuring our view of the stars in that direction. When we look toward the south in the summer and we see this brightest part of the Milky Way, we're looking toward the center of our galaxy. Now I'm going to slow things down to normal speed here again. It's now a little bit past midnight, and There's a star pattern that is one of my favorites in the summer. Um, it's here near the Milky Way. And by the way, these dim stars that you're seeing, like over here in Delphinus, the dolphin, and the Milky Way itself, you can't see in the city. You have to get out away from all the city lights in order to see it. But this star here is bright enough to see in the city. And it's a star called Antares. Now I should probably clear out my constellations before I click on Antares. Antares is another star that looks kind of orange because it's not as hot. And it's the heart of the scorpion, Scorpius. But you may also know it by another name, whether you realize it or not. Because this part here looks like a hook. Have you ever heard, like in an animated movie, a star pattern about a hook? This is Maui's fish hook from Moana. It is actually a real star pattern. That's what the Polynesians call it. Instead of calling it Scorpius, they call it Maui's hook. Now, you might have also noticed a couple of things over here that look like bright stars. And we talked about Jupiter being the second brightest planet. Well, that's what we're seeing here. And then the one to the right of it here is Saturn. So we couldn't see those earlier in the evening at like 10 o'clock when we first started exploring. We had to go later into the night. Now, you're probably saying, well, Mr. Holt, I can't stay up past midnight. I wouldn't want you to. But what we're seeing here in the late night, early summer sky, we can see at a more reasonable time in August. So if you can stay up late this time of the year, great. Go ahead and look for some of these things. But let's set this for, I'm going to click up on the month. That's now July, and this is August. Now, let's say we don't want to go out at midnight. Let's go out at a more reasonable viewing time. Let's say 9 o'clock. Notice that it's not fully dark, but this is the middle of August now. And even at 9 p.m., we can see enough stars to see star patterns. And notice that at 9 p.m. in August, we can see Jupiter and Saturn. And Scorpius over here, although to be quite honest, I'll bet you'd have to wait until 9:15 or 9:30 mid-August to see the dim stars here to form Scorpius. So maybe this is a preview for you of what to look for in August. Certainly the planets are a lot of fun. All right, now I'm going to check in and see some of the questions in the chat before we switch to our other simulation software. I see one, how are Saturn's rings made? Well, remember how I said that the planets were made out of leftover material from when the sun formed? Well, one of the theories about how Saturn's rings formed is that it's leftover material from when Saturn formed. But I think one of the most supported theories is that two of Saturn's icy moons got too close to each other or collided, and it spread that icy material out into that flat area around Saturn. All right, let's, does a planet burn out too? No, planets don't burn out. And don't worry, the sun isn't going to burn out soon either. About 5 billion years from now, we won't want to be here on the Earth because it's going to expand to become a red giant, and the surface of the sun will be closer to us. In fact, it will probably engulf Mercury and Venus, and the surface of the sun will be almost out to where the Earth is. But planets, I mean, all of the oceans will boil away, and the Earth will just turn into kind of a dark cinder. But planets don't actually burn out like a star would do. All right, well, let's go ahead and switch to Digistar, our simulation system that we use in the planetarium. Now, what we're seeing is a view looking toward the south, and early in the evening when it's like first fully dark. The only part that we have actually talked about that's in here right now is actually the like the head of the scorpion here. But what I want to do with Digistar is kind of show you what I showed in the tour, where we can lift off from the surface of the planet and we can head out into space. And that's one of the things that Stellarium can't do. Stellarium is great for viewing what things look like from the Earth, but our Digistar software is great for helping us to explore other worlds as well. Now, one of the things that I want to show you is like where the Earth is in the universe. And so I'm actually going to fly us a little bit farther out. The city lights of Madison are right there. And we've got Chicago and Milwaukee here. But I'm going to move us a little bit farther out. And then I want to turn on the constellation lines. So these are those imaginary lines that we were adding to make the shapes of the constellations. Now, I'm going to do this again when we travel farther from Earth and actually leave the Milky Way. Remember I said that all the stars in the sky that we've been talking about are in the Milky Way? Well, I'm going to show you what part of the Milky Way these stars are in that make the constellations. All right, let's go farther out. Now you can kind of see the moon here, daytime side of the Earth, nighttime side of the Earth, daytime side of the moon, nighttime side of the moon. We're going to go out so fast that we'll actually be not only traveling faster than a rocket can go, but we're actually going to go faster than light. And so, yeah, that would be breaking laws of physics if this was a real journey, but this is just a virtual journey. I've added a line to show the path that the moon follows as it orbits around the Earth. So here's the Earth-Moon system. And now I've added in a line to show the path that the Earth follows as it orbits around the sun. Now you can't really see these lines out in space. Just like the constellation lines, we're just adding them in to show the path that each planet would follow. That's Mercury, Venus, Earth, Mars, Sun at the center of the solar system, the only star in our solar system, and then Jupiter, Saturn, Uranus, and Neptune. Now, if we look at the solar system from the side, you'll actually see that all of the planets orbit around the sun in one flat area. You might have, well, it's kind of hard to notice with just a couple of planets, but did you notice that Venus and Mars and the moon were all three in a line like that? Well, the moon orbits around the Earth in basically the same flat plane that the planets are in. So all of the solar system objects, when you see multiple planets in the sky, they make a line. That's because they're all in that one flat plane. Now let's leave our solar system behind. And notice that we're now so far away from all of the planets that we can't even see the orbit of Neptune anymore. But we still haven't gone past any stars. The stars are much farther away than the planets. Now we're starting to go past some of the closest stars. Now these stars that are closest to the sun, they're the stars that make those constellation figures. Now, if we keep going, we could back up so far away from our solar system that we would actually leave the Milky Way galaxy. Now we're seeing the combined light of about 300 billion stars. We live in a Milky Way, in a spiral galaxy called the Milky Way. I'm going to turn on those constellation lines, and you'll see that all of those stars that make the constellations are just in one tiny little part of our Milky Way galaxy. That's how much of our galaxy we're seeing when we look up at the nighttime sky. Now, if I go out a little bit farther, so that the Milky Way isn't quite dominating all of the scene here, and if I move things around at a different angle, you might see some things that look like stars. I'll point out some that are more obvious, like here and down here. Here. Those are not stars. Those are actually galaxies in our local group of galaxies. And I've got the simulation system set to brighten all of the galaxies as I go farther out, because there are even more galaxies than this. We have about 55 galaxies in our local group of galaxies, but there are billions of other galaxies out there in the universe. It's just that you need a telescope with a camera in order to detect this many galaxies. All right, now we're almost out of time. So I thought I would look again at some of the questions that we have. I see a question, why do we name stars? Well, that's a good question, but think about the fact that we name ourselves, we name our children, and that's so that we can say something more than, hey, you, right? To name things gives us a way to communicate and talk about them. If we just said the brightest planet and didn't have a name, we could say, oh, there's the brightest planet. And yet Venus, calling it Venus gives us a way to kind of personalize it a little bit more. The same with the stars. The sky, to ancient sky watchers, was their clock, their compass, and their calendar. And to have names for them, the stars and the constellations, was a way for them to kind of keep track of it and to pass that knowledge on from one generation to the next. Why can't we see the sun at night? That's a great question. If I look down below my feet, I'm looking down at our planet. You could do the same. When you look down at the Earth, can we see through the Earth? No. And so at night, we can't see the sun because the Earth is getting in the way. Remember, we saw the sun setting in the west because the Earth was spinning? Well, when you see the sun setting in the west, then the Earth gets in the way so that we can't see the sun after that. Now, I see a question about how high up is outer space. And So if we were to go up higher and higher in the Earth's atmosphere, the atmosphere just keeps getting thinner and thinner. And so there's no like height to say the atmosphere ends at this altitude. But since we want to be able to say who has been out in space, out of our atmosphere, they have set up an arbitrary, which means they just kind of made it up, an altitude of 100 kilometers, which is 62 miles, to say if you've gone up that high, you've been out in space. I see another question. How big is the Milky Way? Well, one way to say how big it is would be to say how many stars are in it. And we think it's around 300 billion stars. And by the way, we think that there are at least as many planets in our galaxy as there are stars. So that means that there are billions of planets too. And another way to describe it would be to say how long it would take for light to travel from one end of the galaxy to another, because it's so many miles that it doesn't make sense to use such big numbers for miles. So another distance measurement in space is a light year, and that's the distance that light can travel in a year. Well, it would take 100,000 years for a star's light to travel from one end of the galaxy to another. So we say that the Milky Way galaxy is about 100,000 light years across. Can the Milky Way galaxy be destroyed like stars? We actually, the other big galaxy in our local group of galaxies is called the Andromeda Galaxy. And those two galaxies, our galaxy and the Andromeda Galaxy, are actually being pulled toward each other because of gravity. Now, they're not going to be destroyed, but they're going to pass right through each other, pass through each other again, changing the shape of the galaxies in that process. And eventually the two galaxies are going to combine. But that will take billions of years. So they don't get destroyed, but they merge over time. Now, speaking of time, I see that we are at the end of our time here together. So if you are taking off, I want to thank you for joining us here today. And I hope we get a chance to meet again soon under the actual dome of the planetarium. But if people do want to stick around, I will still try to answer some of the other questions that I see in the Q&A. Thank you for joining us, for those of you taking off. All right, let's see what we have in the chat. We'll answer a few more. Why is the Milky Way galaxy a spiral? That's a good question. And I don't think we can say for sure. And there are probably experts out there that would certainly know this better than I do. But what we think is that as the galaxies merge together to form larger galaxies, they form like a plane, because that plane was perhaps more dense than the other areas around the center of the Milky Way. And as stars are like orbiting around the center of the Milky Way, they pass through regions that are a little bit more dense. And so areas that are a little bit more dense, as things are interacting, as clouds of gas interact, they're going to form more stars. And so we think that the spiral arms are kind of like areas of like traffic jams where there's more stuff there, and so there's more stars. And so the stars in the spiral arms of the Milky Way tend to be younger stars. And so even though stars move in and out of those spiral arms, there are areas that are more dense with more star formation. Oh, here's a really good question. How do we know what is out there past our galaxy? I love those questions like, how do we know? because those kind of show me that you are evaluating the information that you're receiving and questioning it. And I love that. So like when we're outside on a clear night, we can see stars, right? And we're seeing that because our eyes are receiving light that was emitted from those stars or sunlight reflected off of those planets. And so we can detect those stars and planets even with our eyes, right? But you're probably wondering, like, how do we even know that all of these galaxies that I'm showing in this scene are out there? Now, in this computer model, what we have are models of galaxies placed at the location of, in like a 3D model here. You see it as we move around, it is a 3D model. So these are models of galaxies placed at the location of galaxies that have been detected. And they're detected by having like light buckets, light funnels. Our eyes only gather this much light. But if you have a telescope that's this wide, now it's taking this much light and funneling it into your eyes or into a camera. And so if you build bigger and bigger, wider and wider telescopes, then you can gather more and more light. And so the biggest, widest telescopes can gather so much light that we can see and detect very faint things that are very far away. So the short answer is big telescopes with cameras. I see another question. Why does the sky look black or dark at night instead of blue during the daytime? Well, I guess the first part of that would be to answer why it's blue in the daytime. When you go out today and you see the beautiful blue sky that I'm seeing out my window, what you're seeing is blue sunlight. Now, we don't just get blue sunlight, we get all the colors of the rainbow, right? Because when we see a rainbow, that's the sun's light being spread out by the raindrops so that we can see all the individual colors. Now, the different colors of light behave differently in our air, in our atmosphere. Colors at the red end of the rainbow go through our atmosphere really well. And so that's why when the sun is setting and it's way down low on the horizon or even after sunset, the colors that you see in the sunset tend to be red and orange and yellow at that red end of the rainbow. Because even though the sun is low, the light can still transmit through all of that atmosphere. Now, colors at the blue end of the spectrum get scattered. And so you see blue sunlight coming from every direction around you when you're outside during the daytime. Now, when the sun is low enough below the horizon that we're not getting any of that light in our part of the atmosphere, then the absence of that blue light is what we're seeing in the nighttime sky. That's why it looks so black and so dark. It's just the absence of sunlight because the earth is getting in the way. Like um, if we travel home again, when we get back to Earth, I will point out again where we are on the Earth, and you'll see that we're on the nighttime side, and I'll be able to show you how the Earth is getting in the way of our ability to see the sun. Is the sun hotter than the Earth's core? Yes, much hotter. What other types of galaxies are there besides spiral? Eventually, the Milky Way and the Andromeda, when they combine, they're going to form an elliptical galaxy. So we've got galaxies, we've got spirals, we've got barred spirals, we've got ellipticals, and then there are some that are called irregulars. And that's because they look irregular and not spiral or elliptical because they're actually in the process of passing through each other. Now you can see that this is mostly the daytime side. Now I have this set for in the evening when it's first fully dark in Wisconsin. And you can probably see the city lights of the United States here. This is Florida. And so then if I stop it here, there's Chicago, Milwaukee, and Madison. So that's where we would be. Now you can see that the sunlight is not on Madison right now, but it is over here. So if we go down here where we can bring the sun into the field of view, in Madison, we are just out of sight of the sun because as the Earth rotates, we've moved onto the nighttime side. Is there water on Mercury? If there was any water on Mercury, it would have to be in the dark, like permanently dark craters at the north and south poles. And I can't remember. I think that there was hydrogen detected. Don't quote me on this because I'm not sure, but I think that there was hydrogen detected by the Messenger spacecraft in the darkest places that are permanently dark in the craters. And that could indicate that there's water in those craters, but no liquid water would be in the surface. That would just be frozen water. Are there stars in places without galaxies? So like, are there stars in between the galaxies? And I would say almost surely yes, there would be. Because when like two galaxies merge, some of those stars are going to be, they're not going to collide, but some of them could be close enough to each other that a star could be like slung out of the galaxies because it just got too close to another star. And so the gravity of that bigger star could eject smaller stars. But that would be really hard to detect an individual star outside of a galaxy. How many moons do planets have? Mercury and Venus don't have any. We have one. Mars has two. Jupiter and Saturn have 60 or 70. And so the bigger planets have more moons. I don't know if I have a favorite constellation. I see that's another question. Maybe that I just feel like I like all the constellations, and just like I don't have a favorite child. I like both of my children or adult children very much, and couldn't say that I have a favorite. Sometimes, like when I see a constellation in the sky, it brings back like warm feelings, kind of like seeing a friend. Um, and so I have ones like when I see Scorpius for the first time, like in the summer. I really like that, and it brings back memories of summertime. When I see Orion in the winter sky, I always like seeing Orion. Have we ever been in other galaxies? Now, there are a couple of ways that we could answer we. Now, we humans have never been any farther away from the Earth than the moon. So we haven't even been to another planet yet. If we say we humans as sending emissaries, space probes out into space, the farthest we've had is to get space probes out of our solar system. But remember, there was so much space in between the solar system and the nearest stars, it would take us thousands of years to get a space probe to another star, let alone out of our galaxy. Now, if you're wondering if the Earth and our solar system have been to other galaxies, the answer would be no to that as well. Our solar system has only been around for about 4.5 billion years. And in that amount of time, we've just been orbiting around the center of the Milky Way galaxy. All right. Well, I would say that we should probably end it here. You guys have had lots of great questions, and I hope that we continue to explore our questions and search for answers. And I hope that we can do it again under the dome someday soon. Thank you, everybody, for joining us. Thank you, everybody, for your questions as well.